Hi and welcome to Concept Based. I'm John Hepworth. This is probably the last video for Year 11 Advanced Mathematics in Term 1. And it delves into the sine rule. In your syllabus, it does state that you should examine the proofs of the sine rule, the cosine rule, and the area of the triangle formula. I think it's a really good idea to delve into them because I think understanding why a formula is what it is helps you accept the formula for being that way. It certainly helps for me. If somebody just shows me a formula, my first question is like, well, why is that the formula? However, there's plenty of sources out there for looking at proofs like that. What I want to delve into is a particular part of the sine rule, and that's its ambiguous case. Because I find that students can become quite confused about this, forget about it, don't remember that it's a part of the problem, and they can just put an incorrect answer up, not even having considered the fact that the ambiguous case is something that they need to be thinking about when they're doing questions for sine rule calculations like this. So the statement in your syllabus does say use graphing applications or geometric construction to examine the ambiguous case. So I'm going to use a geometric construction. Obviously, the best thing is for you to use a geometric construction, but I'll show you what sort of geometric construction I use to try and help explain it. The program that I've used to do this is Geogebra. So heads up to Geogebra. I love Geogebra. I've done some mathematical artworks, and all of those artworks have been done in Geogebra. I then export them to MS Paint and then color them in. I'd love to share them one day on my channel, but yeah, I haven't done that as of yet. So we're going to try and delve into this sine rule ambiguous case. Let's have a look at what we've got in Geogebra to do that. So here is my Geogebra triangle that I've created for the sine rule. So what I'd like to point out in here is that essentially there is two triangles. There is a blue triangle and there is a red triangle. And in the blue triangle, you can see it has angles B and angle C, and they are opposite angles, sides B and opposite side C. So that seems all fine and well. If we knew 3 of those 4 bits of information, we could find out the missing piece of information. But this side B can actually be swung around on a circular arc. And by swinging it around on a circular arc, what it does is it makes sure that the length B stays the same. So the length B is the length B here. And then I swing it around on the arc and I hit this point here. Now, how did we get this point here? Let's go back over to angle B here. And what we're doing is we're keeping angle B the same while we swing the side. So this angle B can only stay the same on this line if we make it go out and hit that line at that point. So I've now labeled this new side B dash, but it is actually still the same length B. So this B over the sine of this B angle should equal this C over now the sine of this C angle. But if you notice, C never changed regardless of which triangle I had. This is C here, and then this is C here, and C never changes. So if C is never changing, and B's length is never changing, and the sine angle B is never changing, how could the sine angle C change when our formula says that these are all linked together? So if 3 of them are not changing, how could the 4th one, this sine C down the bottom here, ever change? Because it's not part of the formula independently. You can't keep 3 of these things the same and change the 4th. They're linked together. So what can happen is we can get 2 different answers out of this. 2 different answers that provide the same value. What am I actually talking about? Okay, well, let's go back to the previous video that I did, and I spoke about the quadrants in trigonometry, and I spoke about this ASTC thing and said that the sine of an angle is positive in the first quadrant and it's positive in the second quadrant. And I also said that there were these things called primary angles. Then I created what I called a butterfly. So that if we had an angle over here that was obtuse, we could actually recreate it as an angle over here that is acute. I'm going to call this phi, and this big angle theta, where phi is also found here on the other side in that third quadrant. And so from that concept, from the concept that this primary angle is the same as this obtuse angle, and that this quadrant is the same in that they're both positive, we actually can get two answers for sine C, or two values, two angles of sine C can create the same answer. So then how do we know which one we took? Did we take sine of the acute angle, or did we take sine of the obtuse angle? Well, we don't know. We actually can't tell, and it's ambiguous. We would have to go and seek further information from the triangle to try and work out whether or not the angle is acute or obtuse. And if we therefore did go and work that out and it proved it one way or the other, then we would know. But if we couldn't, then we would absolutely never know, because those two are truly exactly the same. The sine of the angle theta, whereas it is an obtuse angle here, is equal to the sine of the 180 minus that theta. And we don't know which one it's going to be. So for example, if theta ended up being, let's say 80, well, a bigger one, 100 degrees, then theta could have been 80 degrees, and both of those would give the same answer. So in my Geogebra program where I created this, I didn't actually measure the sides of the C angles and the C dash angles. But what I'm saying here essentially is that those must be angles that are up to 180 degrees for this to be true. So let's go and have a little look here in the settings, and let's go and change it to giving it a value of this angle. And so the value that it's giving here is 113.8 degrees. So over here at C dash, we should expect something like 66.2 degrees. So let's change the settings and let's change it to its value. And here it is, 66.2 degrees. They are completely supplementary. I forgot the word for them for a moment there. They add up to 180 degrees. And they are ambiguous because of the fact that in our ASTC unit circle for trigonometry, the first quadrant and the second quadrant are both positive for sine, and we can't tell whether we're talking about the acute angle and the obtuse angle. So I don't really want to leave you with a, well, so we just don't know. That doesn't feel great. So what we could do, and we could take into consideration here, is, well, is there any more information that we could look at in the triangle that would give us a heads up? So let's go back into Geogebra and see what else is changing when we change over to this smaller angle. And what you can see is that the length here of the third side that is opposite that A angle becomes significantly larger. Okay, so if this side becomes significantly larger, what it does is it means that all three of the sides end up being around about the same size. You know, it sort of starts to become more like an equilateral triangle. So if you're in a situation where all three sides of the triangle are all pretty similar in size, you're probably in the situation where you've got an acute angle. Whereas if the C side in this blue triangle, I'll just try and select the blue one. You do that via here, just that one's what I was after. So in this blue triangle, you can see this not C side, this opposite A angle that I haven't labeled. This side is much smaller than B and C. And when you've got a side that is much smaller than the other two sides, then the opportunity for an obtuse angle to be created is much greater. Much greater. You can go and draw a bunch of acute triangles and obtuse triangles where one of the angles only is obtuse. And you'll notice that in an obtuse triangle, you will start to find that there's some large side. So in this case, the C side is opposite the obtuse angle. That's what you learn in the sine rule, that the side opposite the largest angle is the largest. And so if this C side is quite large in comparison to this A side and this B side, then C is probably opposite an obtuse angle. Whereas if C and B dash and down here essentially A dash, the red ones I'm talking about now, I'll get rid of that blue and highlight the red. And I will have to also highlight one of the blue sides. So in this triangle, we can see that A dash, we'll call it, B dash and C are all much closer to each other. And that's because their angles are all much closer together because they're all acute. So hopefully that tidies up the ambiguous case for you. If you haven't used Geogebra before, I highly recommend it as a tool to confirm any geometric understanding or proofs that you do. Being able to use it in a way where you can build things that are dynamic as well to prove them to yourself are fantastic. It takes a little bit of time for working out how to do those sorts of things for sure, but I definitely think it's of value because being able to see something do what the rule says it does, like there when I revealed those angles, I did not build this triangle setting those angles at all, obviously. I just revealed those angles knowing that they were going to be supplementary. You know, I could grab this triangle and move it around, and you're always going to see that those two angles here, I'll try and make it 60 nearly exactly, and the other angle will be, you know, like 120 nearly exactly. I'm locked in, you know, I can't not do that situation. So yeah, it's a good way of it proving to you why that is true. That, you know, the angles will be locked in together there and be supplementary because of the proof that we were talking about in the first and second quadrant. All right, I'll leave that one there.